Mechanics. Today we are taking state and equilibrium, episode 3 of Thermodynamics. And let's look at what we have here. Thermodynamics deals with equilibrium states. And when we talk about equilibrium state, what do we mean? Equilibrium is defined as a state of what? Balance. So we are talking about balance. Are we good? That's in equilibrium state, there is no unbalanced potentials and driving what? Forces within the system. When a system is in equilibrium, it experiences no change when it is what? Isolated from its surroundings. So the equilibrium nature of what? A thermodynamic system just means that when you have a system, there should be no what? Unbalanced what? Potentials. Remember, we are talking about what? Energy and what? Energy changes. We can also include what? Forces. So when I have a particular system and the summation of what? Energies or energy within the system should be what? Zero. Are we good? Or the summation of forces acting on the system should be what? Zero. That's where we classify the system to be in what? Equilibrium. We already have this equilibrium idea from what? Mechanics, and we know how equilibrium of what? A system works. Are we good? So there are some basic terms that we have to know and understand when they are being used. Something like thermal equilibrium. When we say thermal equilibrium, what does it mean? A system is said to be in thermal equilibrium if the temperature, we are talking about temperature, is same throughout the system. So I have a system that's made up of what? Water. So I have water throughout this my container. And what thermal equilibrium is talking about is, so if I'm considering this system of water, then temperature at point 1 should be equal to temperature at point 2. The same thing at point 3 and what? Point 4. It should be the same throughout the system. And if the measure of temperature is the same throughout this system, then my system is said to be in what? Thermal equilibrium. Remember, thermal is also talking about what? Heat energy. Are we good? So the heat within the system should be what? The same for it to be classified as thermal equilibrium. Mechanical equilibrium. So this refers to what? Pressure. A system is said to be in mechanical equilibrium if there is no change in pressure at any point within the system with time. Are we good? So let's assume at T1, my pressure was 10 kilopascal. So I should also measure the same 10 kilopascal at what? T2, 10 kilopascal. My pressure should not change with time when I have this system. So if the measure of pressure does not change with time within a system, that system is said to be what? In mechanical equilibrium. Are we good? So from the initial stage to the final stage, the pressure does not what? Change. Phase equilibrium. The system is said to be in phase equilibrium when the mass of each phase reaches what? Equilibrium and stays there. So what this phase equilibrium is talking about is, if this is water as we assumed in a container, then the phase of the water should what? Stay there from what? Point 1 to what? My final point. So if I'm working with this system, it should be what? Water throughout. The mass, the particles will still remain what? Water and stay there. Under any circumstance, if I apply too much heat to this water, we know that what? It will get heat up and it can convert, parts can convert to what? Steam. Now I'll be having combination of water and steam inside the container, and the phase of this system will be what? Distorted. It will be a combination of what? Water and what? Steam, and the phase equilibrium of the water would be disturbed until what? It is what? Homogeneous. Are we good? So phase equilibrium is talking about the homogeneity of the system. Are we good? So if I apply enough heat such that this system now becomes what? Completely steam. It becomes what? Complete what? Steam. So I have steam throughout the system because of the heat what? apply, this system will now become what? Phase equilibrium, because it is only steam what? Phase. Are we good? Chemical equilibrium. A system is said to be in chemical equilibrium if its composition does not change with time. The composition, the particles that make up of the system. Are we good? So this is water particles and they do not change with time. So let's say with time I add maybe a dye to this water molecules, it will change the molecules and the composition will change, meaning this system will not be in what? Chemical equilibrium. A system can be in thermal equilibrium, mechanical equilibrium, but not in phase what? Equilibrium. Let's take note of that. Now the state postulate. There's a postulate that we call the state postulate. The state postulate presents the number of properties required to fix the state of a system. That says that, for example, in thermodynamics, we try to find the state of what? A system. The state of a system. We'll talk about state. I want to know the state of this system. And we have to obey the state postulate to be able to know what state this system is what? Actually inside. Are we good? Is it in the liquid state? When you talk about state, is it in the what? Solid? Is it in the gas? All these are what? States. You just don't look at it. You can't look at it and just say, oh, this is in the steam stage, or it is in the liquid stage, or what? The compressed what? Liquid state. You have to follow the what? State postulate. And what does the state postulate says that we can use to predict the state of what? Any system. The state of a simple compressible system is completely specified by two independent intensive properties. So the state of any system can be determined, or the state of a simple compressible system, we'll talk about that, system can be determined by two or more intensive properties. Remember, the intensive properties, they are properties which are what? Independent of what? Independent of mass. And we saw that example is what? Temperature. We talked about what? Pressure. We also talked about what? Density and the others. So you can predict the state of any compressible system given by knowing two independent intensive properties. So if I give you the temperature and I give you the pressure of a system, you have to be able to predict the state of the system. And we will understand more detail when we are diving more into what? Thermodynamics during the energy analysis for stage. Are we good? So the state postulate help us to use two independent intensive properties. Remember, the word is what? Intensive properties. So you should only consider the intensive what? Properties to be able to predict the state of what? A system. We'll get to a time you know that there was superheated systems. We also have some compressed and a whole lot of what? States. And if I want to know any of these states, the better way is to know two or more intensive properties. It will help me a lot. You get the understanding when we dive deeper. These are just the basis. You are going to be what? Aware of how to use it. Now we said the state of a simple compressible system. What is a simple compressible system? A simple compressible system is defined as a system, any system in which there is no electrical, magnetic, gravitational motion, and surface tension what? Effect. So the system you are considering should be free from electrical, magnetic, gravitational motion, and what? Tension effect. Should be in what? Equilibrium, as we talked about. Are we good? So if I'm considering this whole system, then my system should not have any of this effect. And I'll consider that to be what? A simple compressible system, which I can know the state by knowing two intensive properties. It's very simple. Also, two properties are said to be what? Independent if one property can be varied while the other one is held constant. Example, temperature and specific volume are independent for single phase system. So what we are talking about here, the intensive properties, as you vary one, the other will what remain the same. They are not always what proportional. So the example given is what temperature and what we have specific volume. Are we good? Specific volume. They are not what proportional. You can vary one as the other remains. So this is what we call the state postulate. And with this idea, we are going to solve many questions and understand some nature of what? Thermodynamics. It's very necessary we understand this. Are we good? Now, let's talk about processes and cycles. These are all bases under thermodynamics. So, in actual sense, we have not yet started diving deep inside what? The course. We are just knowing the outlines, understanding terms and conditions. So, a process. In our study, a process is defined as any change that a system undergoes from one equilibrium state to another. That's what we call what? A process. So, for example, this is an initial stage. Let's assume it was in the water stage, and now it is changing from one equilibrium state to the final state. Let's call it was steam. It's just an example. So the change that a system undergoes from one equilibrium state to another is called what? Process. So this is just what? A process. Are we good? It's a process from water to steam. This graph does not necessarily depict what? Water to steam what? Graph. But I'm just making what? An example. So initially the system was in what? A water state, and it went to what? Steam. So I can call this change from one equilibrium state to another equilibrium state as what? A process. Very simple. So the series of states through which a system passes during a process is called what? A path. It's called a path. So this is the process path. We know that water cannot just from one point jump towards steam. It has to go through what? Series of what? Processes. For example, if it is a container, it should what? Receive enough what? Heat to be able to move from what? The water state to what? To vapor. Are we good? And the process of what? Applying the heat, let's assume at this point it was what? 20 degrees Celsius. Let's say at this point it was 80 and degrees Celsius. And at this point we are getting what? Let's say 200 degrees Celsius. So the processes, again, I'm telling you this graph is what? Pressure against volume. We will use it as time what? Moves on. But I'm just explaining process and path. That's why I'm using this diagram. It does not mean this is a water to steam diagram. All right. So the process, the path from 20 to 80 to 200, that's the system has to what? Go through to reach the equilibrium second state. All these processes are what? Called what? Path. That's what we call it, process path. So a path is a series of states through which the system passes through during a process. Remember, at 80 degrees, it will be a combination of what? Some vapor and what? And water. At this state, let's say at 0 degrees Celsius, it was purely water. There was a mixture at 20, there was a mixture at 80, and a complete steam at what? 200 degrees. So the stages it went through from point one to the other is called a path. Are we good? So this is a piston cylinder what? Diagram. So at the initial stage, this was where the piston was. So at stage one, and now there's what? A compression. It compressed the system to state what? Two. Are we good? So this one becomes what? The process parts. At this point, there was what? A stage, or there was what? A state at which the system was in. At this point, it was in a particular what? State. Because at this point, let's say, let's call here A. Let's call this point B. At point A, when you check the independent properties. That's what the intensive properties. The independent properties, they may vary from point B. For example, pressure at point A may vary from point B. So at A it is a different state, at B a different what state, and at C a different what state. So all these states are called what? The paths. It's very simple. And from point 1 to the 2, we call it what? A process. From one equilibrium state to the other. When a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, it is called quasi-static or quasi-equilibrium process. Are we good? So this is what we call a quasi-equilibrium process. We will explain more about the quasi-equilibrium process. So the process talking about a slow what movement such that we will consider each state to be what in equilibrium. I'll talk more about the quasi-equilibrium. Are we good? All right. So this explains process and cycles. We also have some processes here. So we'll be using what we call the ISO to clarify constant what processes. So the prefix ISO is often used to designate a process for which a particular property remains well constant. So let's take a look at this. So for example, when a particular state is what constant, we will call it iso something, iso the other. So when you say isothermal process, the moment you see thermal, it should help you. So this is a process during which the temperature remains what? Constant. It's talking about temperature. When we were talking about equilibrium, we saw what? Thermal equilibrium. That's what equilibrium states. But here too, we are talking about what the process, we are talking about process. So when a system is changing from one equilibrium state to the other, and throughout the states, throughout the journey, temperature remains what? The same, that process is called what? Isothermal process. Are we good? What about isobaric process? It's a process during which the pressure remains constant. So when a system is changing from, let's say, water to steam, and throughout the process change, pressure remains constant, that process is called isobaric process. Isochoric or isometric process. In this process, specific volume remains constant. Remember, we are talking about specific volume, small v, which is the volume over the mass. We'll talk more about all these things. They are very simple. So the volume or the specific volume remains the same throughout what? The process. It is called isochoric process. Polytropic process. This process satisfies the relation PVN equal to what? Constant. So we also have an equation we'll be dealing with. PVN is what? Constant. And we call it what? Polytropic process. All this, I don't want to talk about them into details because they are coming and we will understand them very what? Deeply. They are important, and as we are just tackling the basis, I don't want to add the details here. We will talk more in the other what? Episodes. A system is said to have undergone a cycle if it returns to its initial state at the end of the process. Thus, for a cycle, the initial and the final state are what? Identical. So a cycle in thermodynamics, when we are talking about a cycle, it means the initial and the final state are what? The same. Are we good? When a process starts from the water state and is heated to a point, it is heated to a point and it is cooled back to water. This process is called what? A cycle. Are we good? It started from water, it increased in heat, and at a point there was what? A condenser here that cooled the temperature and went back to water. All this process is called a cycle because it started from water and came back to its initial state, and we call it what? A cycle. So in any analysis, when I say a cycle, you should understand that that system started from its initial state and ended the same thing as its final state. Now, the last thing we'll be talking about before we enter episode 4 and start with what our main analysis, energy analysis. From the episode 4, we'll be solving questions, diving deeper, making energy equation analysis, and it's interesting, trust me. So, our last thing we'll talk about is the temperature and the zeroth law of thermodynamics. All these are objectives from episode 1 to episode 3. They are all objectives, they are all understanding basis, and they are important. So, what does the zeroth law state? It states that the zeroth law of thermodynamics states that if two bodies are in thermal equilibrium with a third body, they are also in what? Thermal equilibrium with each other. Very simple. I like this law so much. It says if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with the body. Are we good? So let me explain it further. So let's say these two bodies, body one and body one and body two, they are in contact and they are in what? Thermal equilibrium, heat. So the amount of heat here is what? The same. Heat energy is what? The same between the two. Are we good? So let's say since it is energy, they are all having 10 what? Kilojoule of what? Heat energy inside them. And it says if these two bodies are in thermal equilibrium with a third body, they are also so the moment I add a third body to this, to them, third body, this third body will now be in equilibrium with all these three. Are we good? So meaning either they share the amount of what energy among themselves so that each one will get a reasonable amount for them to be in equilibrium. There's no way these two were in equilibrium. I add a third one, each will be in 10, 10, and the third one will be in what? 5. It won't work. They should all be in what? The same. And let's look at the implications of this. What does it help us? It serves as the basis for the validity for temperature measurements. So upon this zeroth law that we are able to measure what temperature by placing the third body with a thermometer, the zeroth law can be what? Restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in what? Contact. So for example, when you go to the hospital, the thermometer is placed in between the arm and what? The armpit. The arm comes what? A thermometer, and it follows what? The armpit. So initially, there was no thermometer between your arm and the armpit, but these two were in what? Thermal what? Equilibrium. So your temperature was maybe 20 degrees Celsius. Are we good? Now a thermometer which was a third body was brought in between the two. So the three are now in contact now. Are we good? Now the thermometer is going to read the temperature at which the two were initially what? Having. So have you seen how thermodynamics is what? Helping us. So it is the basis from the zeroth law that we brought what? The thermometer for temperature measurement. Are we good? So the zeroth law is also making an account here that if two bodies are in thermal equilibrium, the third one can even have the same reading when they are not in contact. Are we good? We can talk about the recent thermometers, that's what the infrared thermometers. They can just show it on your forehead and it will what? Detect your temperature because it can be able to what? Read no matter what the distance if they are not in what? Contact. But more specifically, I would like to stay with the first one, which says that two bodies are in thermal equilibrium with a third body. They are also in what? Thermal equilibrium with each other. And that's very simple. So with this, we are done with the basis for what? Thermodynamics. And now we are going to dive deeper into the course, energy and energy analysis. Look out for the other episode to enjoy the calculations. Thank you.